Well, hello. This is my turn to give the presentation about my final project, which is named Research of Flow Control Regulation in IP Backbone Network. And my name is PengHuang. Hope you enjoy it. And first, let's see the content of this presentation, including the first part is the background introduction, and then I'll tell you something about the algorithm design, because I have multiple algorithms here. And then the simulation design, which is kind of the environment settings. And finally, we'll talk about the flow control architecture design, which is the main implementation in this project. Let's first see the background. Well, actually, there are mainly two problems to define. First is the traditional IP backbone network. It has some defect in it. Well, actually, in the traditional IP network, the flow control strategy executed independently in each node is actually a kind of single node and single link control method. Well, when some links get overloaded, instead of routing to these alternative routes, they will drop the packet, which is kind of a low utilization of the bandwidth. And then it is incapable of delicate control. What does it mean? Actually, it means the routing function is actually completed by matching the entries of aggregate mask table. The routers can neither know everything about every IP flow, nor split the sync flow actively, as to control the specific routing method of the IP flow inside the sync flow. Then why do we need SDN? It's more flexible, and it offers us more options on the infrastructural devices. Well, because confronted with the introduction of new technique, virtualization, and QoS, service of qualification, and some other challenges, using the software programming way, which is the SDN stand for. To implement new network protocols and functions are actually the most valuable point of the SDN. So that's why we need to use it. Then let's talk about the algorithm design. There are mainly two parts. First is a certain problems analysis, and then the real design of the algorithm. Well, let's first talk about the problems analysis. First, a traffic scheduling. This project is mainly a traffic scheduling solution based on the SDN architecture. Two arguments need to be noticed, which are the input and output. The input here is to include the information of network topology, which is the physical topology, the real-time workload on links. This is kind of a simulation of the bandwidth and the workload. And the sync flow routing and stream size is kind of similar as the previous one, as this one, the workload, an IP address and the stream size, and relationship between the sync flow and the IP flow, which will be talked about later. And the output, that actually information of the sync flow, original routing. It should be the route actually, an updated route. I mean, this is the old one and the new one. And secondly, we'll talk about the staged algorithms, because the main function of the algorithm in this project is to distribute the business flows in the congestion link to other alternative links, so as to achieve the load balancing to achieve the load balancing as to solve the problem of the local congestion. So there are some problems because some streams may be so large, so we need to split them into smaller pieces. And secondly, because the size of the stream is actually non-fixed, so the algorithm need to be staged. which means phase by phase, to be adjustable to this flexible length. Well, this is actually the overview of architecture of the first algorithm, which is named the phase extension path algorithm. Well, in the step 1, the congestion link detected. If there is any congestion link, it will trigger this module, trigger the algorithm, and then it will sort the links in descending order according to the proportion exceeded. I mean, some amount of it have exceeded the limit we set. So this amount will be used to sort these links. In step 2, need to determine the current granularity size, which is K. It is not mentioned here actually. Yeah, it's not mentioned here. It's K. Well, we set the K to be 2 multiply n. N is a random number between 0 to 8. Well, if this limit is a kind of the limit, granularity is the limit. If this limit is reached, then the output the migration scheme. Otherwise, we'll continue, go to the step 3, which is here. We need to determine if there is any congestion link, because here is just a trigger. Maybe after this, there's no such congestion link, right? We need to detect if there is actually a congestion link. If no, then the algorithm will end and output the result. Otherwise, we'll continue to step 4, which is here. In step 4, we'll first traverse the congestion links, all the congestion links, and pick out one of them. If all links have been visited, then return to step 2, which is here. Follow here. Otherwise, we'll continue with step 5. In step 5, first we'll use the start and end points of the current groups of congestion links. But actually, because each link are connected with 2 nodes, which is the start point and the end point, we use these points to group those links up for further adjustment, because we can treat them as a same group. Then in step 6, we'll choose. No, this is step 6. Let me see, where is it? Give me a second, sorry. In step 6, we'll choose K alternative shortest path according to the start and end points. Well, if no alternative path exists, we'll continue with step 10, which is here. Otherwise, we'll go to the step 7, which is here, the next step. Oops. Sorry. Well, in the step 7, we first split the sync flow according to the current split granularity, which is defined here, actually, which is also the limit. And then sorts the after split sync flows in descending order according to their bandwidth requirements. Then we go to step 8. We use the remaining maximum flow greedy algorithm, which is used to choose the route with the largest bandwidth to put the flow and update the network. After that, if the load on the current congestion link is lower than the threshold, we return to step 4, which is here. Otherwise, we'll continue with step 10. In step 10, actually, we extend to both ends of the congestion link in accordance with the start and end points. We'll then sort the shared congestion links in descending order pick out one of these links with the largest workload and extend it. Well, if it is an edge node, because we have a core node and edge node, if it is an edge node, then we do not extend it. This is actually the second algorithm, which is called the phased combination path algorithm. It's the same actually for some of them. Just like the first part will detect the congestion link, and the second part determine the threshold, the limit of the granularity, and the third part detect if there is a congestion link actually. And then there is something different. In step 4, we'll first find all sync flows in each overloaded link. Then we'll obtain intersection of all of these sync flows within each overloaded link to generate groups of sync flows. Flows within each group pass through the same set of congestion links. But this can be called a group. How we organize the group. And then with the step 5, we traverse all the sync flow groups. If no such group, we'll return to step 2 here. Otherwise, we'll continue with step 6. In step 6, we actually generate groups of flows. Flows within each group have the same source and destination IP address, which is called the SD address. Then step 7, we'll traverse all these generated groups. And then step 8, the same as the previous one. If there are any, we need to pick out k alternative path according to their source and destination access point. And in step 9, we'll split the sync flow according to the current split granularity, which is almost the same as the previous one. And the 10, the same algorithm mentioned before. And the final step is to load the current congestion link. If the load of the current congestion link is lower than the threshold, here we have a threshold, then we return to step 5 here. Otherwise, we'll go back to step 7. Well, this is mainly much about the algorithm design, and we'll talk about a simulation environment. This project I simulated 34 nodes, including 9 core nodes and 22 access nodes, and the rest are user nodes actually. All the 9 core nodes are fully connected with the bandwidth of 100 gigabytes, while the 22 access nodes are connected only with 3 core nodes with the bandwidth of 50 gigabytes. Where each node has its own IP subnet. And the sync flow design, this is actually about the size of the sync flow. There are kind of 6 levels, which are shown here. And then the IP flow design, it is actually the concerned with the IP address appointment and the size of the IP flow. And finally, we come to the matrix. There are kind of 4 metrics we can use to value this performance. The first one is the sum of link traffic. With this element, we can get the total amount of bandwidth obtained by the algorithm, and thus the estimated number of hops. The smaller the number of hops, the lower latency it is. The second one was the variance of the bandwidth used in the links. We can analyze the effectiveness of the load balancing. The smaller the variance, the better the balancing. And then the number of entries modified. Number of OVS entries updated by the rerouting. The less the modification, the less we adjust the table, the more stable the underlying network is. Excuse me. But finally, the success rates of migration, which is kind of the ratio of congestion link load of which the ratio of congestion links load of which falls below the threshold. The larger the ratio, the less congestion, the better the QoS. Then we come to the flow control architecture design. Is the final part, which is the main implementation of this project. It contains mainly two parts. The first is the control layer, and then the flow control workflow. Let's talk something about the control layer. Well, first we need to see that it has a flow control unit. But the central flow control module, I think. Oops, sorry. The central flow control module is composed of algorithms which are used to reduce the link load, which are the load reducing algorithms we designed previously. When the module is triggered in the overloaded link, one set of overloaded links will be input into the algorithm, and the information needed for the synclo migration will be output. And in this proxy module, multiple modules will work together to function, including a periodically called API module, the congestion detection module, the sync flow and IP flow transformation module, and some other things like that. And finally, the database module is included in the unit. And secondly, we use the floodlight controller. This is the architecture of it. Actually, we can see here there are mainly three APIs included here. In the API of obtaining the link load and routing tables, the command fetching dispatching module will be called on, which is here. Command fetching and dispatching, which will pass the commands via the OpenFlow protocol to the OVS here. Excuse me. And the OVS will respond to this command received and upload related information to the floodlights. Oops. Yeah, to the floodlight. The flow table dispatching API, which is here, will just dispatch the flow table to corresponding OVS via the same OpenCV protocol. And the last part is about the flow control workflow, how it works actually. It has mainly two steps. First is initialization. Well, when the generation of the topology has been finished in floodlight controller, which I mentioned before, it will actively call on the topology information API to write the tuple related information to the database. And once this new flow routing request appears, the floodlight controller will find a route within its own module, and call on the API flow information API, the IP flow information API, to start the initialization of the IP flow information module and write the IP flow information to the database. After that, the flow dispatching API will be called to pass the IP flow table to specific OVS. And after the initialization, we'll have the stabilization. We will first run the periodic called API module to call on the link load obtaining API and the routing table obtaining API. Then the command fetching and dispatching module, which will pass the commands to OVS via the OpenFlow protocol, just as we mentioned here. It will call on here. And when the link load information is received, the congestion detection module will be triggered. Sorry. We'll first write the congestion information to the database and then determine whether there is an overloaded link. If yes, then the algorithm in the flow control module will be triggered to do some flow control processing. When the information of the routing table is received, it will first be processed by the sync flow transformation module. This will be transformation actually. To get information of all sync flows, sync flow routings, and size of sync flows, and other things like that. Finally, triggered by the congestion, and then triggered by the congestion link, the load reducing algorithm in the central flow module will communicate with the database. If both the link of the link and the flow here includes the sync flow and the IP flow information have been updated, then they will execute the algorithm mentioned above and get the output of the information needed. The flow generating module will transform the sync load information which you get in the previous step to sync flow tables, transform this information to tables. But in the end, the flow table dispatching API will forward the information of flow tables which is generated in the previous step to corresponding OVS via the OpenFlow protocols. And with this, everything is done. Now let's see some demo of it, how this actually works. This is the path we have. We can see something about the nodes. Here's the node number, the start IP, the end IP, and the status, because I've set some of them on and some of them off. There are many 31 nodes. And we can see something about the links. Here there are actually 102 links. This is the size of it. This is the capacity of it. The source, the link number, this is the sync. Okay. This is what we have here. Hope it works. Oops, sorry. I think it should be like this. Okay. It's GPK. I have Chinese command here. Okay, hope it works. It takes some time. This one here is the granularity of the split flow, and this is the number of overloaded links, and this is the same. This is a test of different number of different granularity will lead to different overloaded links. This is the number of modification entries, the flow times the routing table entries added. This is the number of it removed, and this is the total number of them. The sum up number of the add and the remove. This is about the combination algorithm. This is the no combination algorithm. You can see here it takes more steps, more modifications. Then we have the extension algorithm. Even less steps needed. No extension, even less step. Then we have the half extension here, which is kind of here like this, and that's it. Thank you for your attention.